And take your time setting up. I'll just let people in so that they know that it's the right link. Yeah.
Cool.
Turn my video. Hi, everyone. Welcome. Kesha's just setting up while we are getting ready. If you're someone who's in CS 245, could you write that in the chat? I'm trying to keep track of attendance for that. Awesome.
Okay, we'll give just 1 or 2 more minutes to for people to join in. In mid-time, we can go through today's check-in question, which is, yeah, so since you have your exams coming up tomorrow, just a question like, what do you do a night before the exam to de-stress yourself? Maybe you can put the answers in the chat. Oh, nice. Just the night before you start studying, Sarah.
Yeah, it just worked out that way this time because we also had a project due tonight. So, and I just finished that. So the quiz was sort of secondary.
A lot of things going on at the same time. Busy time of the year.
Oh, yeah.
Anyone else who would like to share? Just unmute yourself. Feel free to just unmute at any point. Cramming. Grace is cramming. Mia, what do you do? Mia, are you with us? Oh, okay. So Claire says the night before exam, I try to de-stress like that. Myself, like I know most of the time. Give myself credit. Yeah, that's a good way to build up confidence. Night before I like to meditate and or watch an episode of TV to relax. Yeah, I to do this. I watch some favorite episode of mine to just relax. Oh wow, yeah. So the extra practice problems. Yeah, I think to put things on your short-term memory is the best way to go the night before exam. You can easily extract it from your memory. Okay, so yeah, we would start the session then. So we are the Women in Tech group, and our aim is to empower experience for every participant who supports this community. And yeah, the code sessions are such that you gain more technical skills, practice, and learn more about your internship opportunity. Are we already recording, Sarah?
Yes, we are.
Cool.
And Kesha, if you could put the slides on presentation
Yeah,
mode.
sure,
Yeah.
sure.
Thank you.
So today we'll be going through searching and sorting, as that's the main topic for even the exams for 245 people. And if you have not already joined the Slack channel, do join it. It's AlgoSWIT on UFSCS, since we will be posting the slides and every material or discussing the problems over there. So make sure you join the Slack channel. And today we'll be going through what are the different categories of sorting, some of the main algorithms, and where exactly are they used. Like a use case could be binary search, and some lead code problems on the topic that we studied today. So before we start, so sorting algorithms have a lot of different categorizations. So there is no unique way that you can bucket them all together. You have like bucket sort or selection sort, insertion sort, different types of sorts. So how do you actually compare like which one is better than the others? So there are certain matrices that people have chosen to put them into buckets, and there are about 6 to 7 matrices that we will be discussing today. The first one is number of comparisons, like how much time does it take depending upon the input to run for the algorithm. So you compare each element as a key and check it with the rest of the elements in the input. So that's how many times you make the comparisons. Uh, uh, that could be your time complexity. So for sorting, I think the best case that you can get is order of n log n for any input, and the worst case is order of n square. If anybody wants to just raise hand or ask any questions, just feel free to unmute in between the sessions, like on any slides if you have any question.
And Kesha, I'm going to jump in since I know you're going to be explaining some of the background right now. I made a kind of like note-taking guide for you all. This is actually based on when I had Berzon's class over the summer. I had CS245. And since Kesha's explaining a lot of the time complexity and space complexity, I figured it might be nice as something for you to do before your midterm to just kind of think about the different sorts and think about how you would implement them. I've summarized the time complexity and space complexity there. I also have like whether it's stable or unstable, if that's something you went over in your class. But that's just a guide. If you want to use it, you essentially are just going to go to File, make a copy, and then you'll have your own copy to write in. So that might be something useful to do while Kesha goes through this.
Yeah, that would be good. Thanks, Sarah. That's amazing. Yeah. So the next one is the number of swaps. That's also called inversion. So whenever you have a comparison, say 1, 2, 3, 4, 5, 3, 5, 4. So here there is just one inversion, that is 5 and 4. This is like how many swaps you have to make to make this array sorted, just one swap. So that's how the swaps comparisons are. And memory use is, there are some algorithms which use external space and some which just use the array which is given in order to just swap and put it in the right order. So depending upon the external memory usage, you could have either order of n external space, or best could be like you do it in place without using any additional memory in order of 1. The next is stability. Stability means like the relative positions of equal inputs remains the same. Like here in this example, you see 2 star and 2 hash is in this order, like star comes before hash, and when it gets sorted, it's also the star before hash. So you might be thinking like 2 is just 2. Why you need a comparison between like two numbers? Had you put like a 2 hash or 2 star, it wouldn't make a difference as such. But just imagine like these are numbers, but it could be students categories, and you compare it by say their marks. Then you want like the students uh, who are already before, say the students are in sorted order, like we get our participants over here, I guess. Yeah. We have this Grace, Joy, and Joshua. Imagine there is one more Joy over here, and the marks of Joy is 95, and the marks of other Joy is say 97. Then the order of those two should remain the same. So think about more broadly in terms of objects and not just numbers, then you can appreciate the concept of why stability is important. And there are some algorithms like insertion sort, bubble sort, and Reddick sort that will see later, where you can just try to see whether the stability applies or not going forward. Then the next is recursive versus iterative. There are some algorithms where you call a subproblem on the same input, make a subproblem and try to divide and conquer and try to do it in a recursive way, and some where there is an iterative way where you write while loops and iterate through all the elements and see, like bubble sort. And there is sometimes also a combination of both a recursive and a iterative way, like a merge sort, where you first divide and then conquer it together with an iterative version. The next is adaptability. So it means like your input, whether it's already sorted or partially sorted, then it could also affect your runtime. Like for quick sort, if it's already sorted, then your pivot would always be the last element and you have to compare to all n elements. So then it would be order of n square in the worst case. And for bubble sort, if it's already sorted, then you would get order of n as the best case, because you don't need any swaps and no second loop would be needed in order to check for the other elements. So yeah, that's the case where it would be even better than order of n log n. So yeah, adaptability means if it's already sorted or partially sorted, then you can get a different runtime. Other adaptable sorts are insertion sort, and non-adaptable ones are selection, merge, and heap sort. Any questions on this category before we move on to the actual sorting algorithms? Okay, yeah, so let's go through then the different sort of sorts. We are going to go through bubble, selection, insertion, quick merge, counting, which is also called bucket, and Reddick. So 7 types of sort we'll see in the next 10 to 15 minutes. Bubble sort is where it cascades as a bubble. So you can imagine like you are given an input array like E, B, C, A, B. And to make it in a sorted way, you try to check through all the elements and bubble it to its right position and try to put the right element towards the end, and then consider the sub array as the one which is remaining. So for example, here you just compare each of the element with its next element, E with B. You see that E is greater than B, so you just swap it. Then E with C. So B would be the first position, E would be here after the first swap. Maybe we can just try to copy and just go through it like on a sketchpad. Yeah, so for example, if we are given this sort of an input, so for the first case, E and V is compared with each other. So V is smaller than E, so it would get changed to like this. Then E and C are compared, so C is again smaller. So we get C over here, E over here. Then E is compared with A is again smaller. and E would come here, and E and D is again compared. So D would be here and E would be here. So we see B, C, A, B, and E. So at every in each iteration, you will see that the max element would be put towards the end. So E position is already set, and your next checking loop would be to from 0 to 4, 0 to n minus 1. Then in the next iteration, you can observe that D is already set at its right position, and your next set would be 0 to 3. So at max, in n iterations over here, you will see that it's at the right position. And for each iteration within itself, also you have to check through n elements. So then it would be order of n square in the worst case. But what if it's already sorted? So you can just try to make a Boolean variable like sorted, and then try to check whether it's already sorted or not. So you get an input like A, B, C, D, E. Before going through the loop, you have a Boolean called sorted equal to false in the first initiation. Then when you go here in the first loop, you make it true. And then you try to compare each and every adjacent element. Since they are in sorted order, there won't be any swaps that would be possible. So it won't go into the next loop over here and won't be false. So it would stay true only. And when it goes to the main loop, since it is true, it will just exit out of the loop. So the next time it doesn't even need to check for the remaining elements. So just with one iteration, it would be done. So that's why in the bubble sort in best case would be order of n. The next is any questions on bubble sort? Okay, the next is insertion sort. So insertion sort, you can imagine like playing a deck of cards, and for every new card, you try to insert it at its right position. Like we'll just see example of how it goes for this. Yeah, so in the insertion sort, you have the first element say E, and you think that you have just one card in your hand. Then in the next step, you get two cards, E and V, and you try to insert the new element, which is B, in its right position. So B comes at the first place where it is lesser than E. So these two positions are fixed. Just a second, I will just plug in my charger. Yeah. So V and E are at its right position. And now you check for the new element, which is C, and try to see where do you insert it to make it sorted. So C comes between V and E. So this is where B, C, and E are sorted. Then you check for the next element, which is A, where A's position is just right in front of B. So A, B, C, D, E, you get. Then check for D, and D is between C and E. So for each, so you check for the length of the number of elements, which is n, and for each comparison, like say you want to find the right position of B. So at max, you have to check for n elements before it. So then again, this is also order of n square. N for the total number of iterations, and in one iteration, you check for n other elements. So that's order of n square for insertion sort. Any questions on that?
I had a question. Oh yeah, go ahead.
Yeah,
Grace.
sure.
Oh, thanks, Sarah. Just the way that you had shown that on the sketchpad, like if you consider on the first, like the first pass as like n iterations, so you kind of look at it by like I'm trying to say that it looks like between the for loop, the iteration makes it look like a n by d, like it almost looks like a matrix notation. Is that
Mhm.
like kind of how you get the n squared for that? Like if you think about it like that?
Yeah, sort of. So this is big O. So for the first time, it is one only element that you are checking before it. Then for the second iteration, there are two elements that you are checking before it. And for the third, it's three. So it's all summation of those. So like maths, you have 1 plus 2 plus 3 plus up to n. You get n into n plus 1 by 2, right? So that's where order of n square comes. So you can visualize it in two ways. Either you can do mathematics or see as a matrix of how many steps you do before it. Did I answer your question or is you still confused?
Oh no, it was a very helpful like visualization.
Oh, okay.
But I just wanted to know a little bit more behind it. Thank you.
Yeah. Any other questions? I think someone else also had.
Oh, I was just gonna ask, so like looking at like the second row, for example, so we're at C and we're comparing it first to B, then comparing it to E.
No, I
And
think
so,
we go in the reverse order where we compare
okay,
it to E first and then B.
okay, so that's where the swap's happening, like C
Yeah.
to E. Got it. Okay, yeah, that I see that now. Thank you.
Yeah. Yeah, thanks for clarifying that. Any other questions on insertion sort? Okay, if not, then we move to the third one, which is our selection sort. So selection sort, you can again imagine like playing a deck of cards and you get like 5 different cards. You see which one is the minimum and try to put it at the first place, then see which is the next minimum and try to put it at the second place. We'll again see this with an example. Where- Okay, so we have this E, C, D, A, B. So you want to find which is the minimum out of it, which you would find it as A, and try to just swap once. So if you see the number of swaps are maximum limited to 5 over here. We'll see how. So the first swap will be between the minimum element and the position, the element which is at that position. So E and A. So E comes over here and A goes here. And now your working set is just this much. Now you see which is the minimum element in this working set. So it would be B, and you try to put it at the second place and just swap it with C. So A and B are at its correct position. And now your working set is only this much. Now you check which one is the minimum out of 3, which is C. So you put it at the third position and swap it with the last. And now you see A, B, C are sorted. So in each, and now D, E is only remaining. And in the next iteration, you see which one is minimum in this set. D is the minimum, so you swap it here. So D comes here and E comes here. And since there's just one last element left, that would be the minimum. So here maximum number of swaps happens only n times. And in each step, you find which one is the minimum and put it at the first place in the remaining subset. And every time you reduce the set by once. So again, for this, you need to run n times to check to find which one is minimum. And for each, to know also which location is minimum, you need to check for the remaining n elements. So for the first time, you need to check n minus 1 elements. The second time, n minus 2, up to like 1 element. So that's again order of n square, which goes for the selection sort. Any question on this?
I like selection sort because
Yeah.
it's the easiest to visualize.
Yeah, I guess it's very easy. I think, yeah, the tricky part comes now with the merge and quick sort. Okay, so with the merge sort, it works as a divide and conquer. So let us just first see its code and we'll come back to the visualization. So what we do in merge sort is try to find a midpoint and apply recursively merge into two parts. It's left part, which is left to midpoint, and then mid plus one to right part. So in two halves, we recursively apply merge sort till it breaks. And then once you have the minimum broken individual elements where you get just one single element where mid is equal to say left or mid plus one is equal to right, that's when you start merging the elements together. And in merging them together as well, we have to so when you break it the maximum number of times that you can break is like order of log n. Do you guys realize like why it is log n? Can you visualize it as a tree? Was it taught in the class? If not, then okay, we'll see why is it log n when it comes here. And the merging part could be like if you extend it to more than order of n square, then it would be the worst case would be n square. So you have to ensure that the merge also happens in order of n. So that's the most beautiful part of divide and conquer, where how you get it order of n log n for every case is quite interesting. So we'll see this example. Okay, so before that, maybe we'll just see how it breaks down. So E, C, G, A, F, and B and D. This is the input which is given to you, which is 0, 1, 2, 3, 4, 5, 6. Total 7 numbers are there. So then half would be approx 4 and 3. So the first breaking point would be E, C, G, A. And the second breakpoint would be FBD. And you recursively apply the merge sort again on the left and the right part. So then for 4, it would be broken at 2, which is EC and GA. And here it would be just because the first part is more, so FB and D. And again, this would be broken into E and C half parts, G, A, F, B, and D was already alone, so then it would stay as it is. So that's how we get the individual components, the merge part, like till here, it's done. Now the merging happens when it's broken into the most individual atomic parts. And merging is you compare two elements at a place and try to see, try to put at a right location. So here say C and E comes together and A and G comes in the reverse order. FB again reverse order and D stays as it is. So let's look at a more longer example to see how the merging happens. So you have two different parts, CE and AG. So one possibility is you just append it together, say C, E, A, G, and try to apply any of the sorts that we saw, bubble sort, insertion sort, selection sort, try to do anything. But then maximum you can do is order of n square, as we saw in the 3 previous elements. So if you do order of n square over here and dividing this is log n. Okay, we'll park this aside. Why it is log n, just assume it's 2 right now. I'll just come back to it. So this would be order of log n and this would be order of n square. Then maximum would be order of n square log n, which is like worse than even the previous ones. So now our target is to make this as order of n and let this as a order of log n. So then the complexity would be n log n. So our challenge over here is to make this order of n. So how do we do that? So we maintain like two different pointers. and an additional space of memory where we keep on storing the elements as the minimum is encountered and both the lists are not exhausted. So here, if you have two pointers, say I and j, the smaller of I and j is j. So you just put it in the additional memory and increment j. Then you check G and C, which is the ith and jth position, and see the ith is smaller, so C is smaller, you put it C over here. So you just have to loop through both the sets at most one time. So you're not comparing within the loops what is the right order. Because once you come over here, you would ensure that the list by itself is in the right order. Because the previous step would ensure that whatever you have in the individual list will be in the sorted order. So you are not comparing within the list, only you are comparing across the list, which will ensure its order of n. And to know why it is log n, you can just imagine it as a tree which is going down, and each tree is broken at max into two steps. Like every element, like 7 is broken into 4 and 3, so two steps, again individual two steps. So then the height of the tree would be the maximum time that it takes, and height would be like, so this would be total of 2 power n, and so then that would be a log n times that would be taken. So 7 would be maximum of log 7 base 2 times happening. Any questions? I think this is a little tricky, but yeah, not a straightforward. Any questions on this?
No, the visual is really helpful. What makes this one the most complicated to implement is that, yeah, just implementing those pointers, making sure that one of them hasn't run out. That's what makes the implementation super long.
Yeah, that's true. The merge part code is quite long over here. You have to check whether, like, initially both of them are not exhausted. So I and j, I is less than m and j is less than right. So the first part is still left to mid, and the second part is from mid plus 1 to right. And the end condition will make sure that both of them exist. And then it would come out of the loop when at least one of them has reached the right position. So either I is equal to m, I is greater than m, or j is greater than r. Either of this condition could be true. So then you write a piece of code for both of them to ensure that the remaining parts are put back into the temporary array. And then just copy back the temporary array into the final array.
I have a question for you all, like, while we're on this. Are you allowed to, like, any materials going into your midterm? I'm just curious if they expect you to, like, come in ready to implement merge sort. Grace, I saw you nod. Like, are you allowed like a half sheet or something?
I'm pretty sure we can just use all of our notes.
Okay. Okay, good to know.
Fine. Yeah, that's fine.
Yeah, I mean, it would also be a really like harsh interview question if someone like, you know, gives you merge sort right away, but I would try to make sure that like, as you go through whatever implementation you've been using, that you understand it. And if you understand the concept of it, you will be fine. It is one of the more complicated ones.
Yeah, that's right. Understanding the code by itself is more complex. And mostly what happens in interviews is you are allowed to use the inbuilt libraries available with the Java. So you have C++ STL libraries, or Java has their inbuilt arrays function, collections has their sorting already available. So then when it comes to interviews, most of the times, like if it's not a particular question related to sorting, but a problem related to your thinking capabilities, then you can just write one line of code, say arrays.sort, and just passing your array or the starting index and the end index, and that would work perfectly fine. I think most of the lead code questions also that I do now or in the contest, I just write one line of code, and I think that whatever implementation that Java or STL has given, it's the best optimized one, and I don't need to go into it. But yeah, this is just for the basic foundational understanding of how it works internally. So yeah, it's useful.
Okay, thank you, Kesha. Good to know. And Claire said in the chat that Berzon's class does not allow any materials. I personally had him. I know, or I don't want to say it for sure. Obviously, things can change, but I don't think he's going to ask you to implement merge sort like on the midterm from scratch. He might ask you like, hey, like he might give you some part of the implementation and ask you some questions about it.
Yeah, I think we have a practice question right on merge sort, which we'll do in the second part of lead code. It's one of them, I think, is on the merge sort. That would be quite fun.
Awesome.
Yeah. Then the next one is quick sort. So yeah, quick sort is again a recursion way. So what we do is we divide the array, but instead of putting it into half, we select a pivot element first at the first step. Generally, the pivot is the last element, and try to divide it in such a way that you put this element at its correct position, and all the elements which are lesser than it comes to the left of it, and which are greater than it comes to the right of it. So as you see, the last element chosen here is D. All the lesser elements are C, A, B, and greater are E, F, G. You can also observe that the relative order of positions is maintained over here. So C comes first, then A comes, then D comes. The order does not get intertwined in between. So it's one of the stable algorithms as well. And why just select the last element? Like you can also go from first element, that's also not a condition, but the idea is like if you take one particular format, then there is a high possibility that it's a randomized thing. So you might divide it into two unequal subsets. So had this array been already sorted, like A, B, C, D, E would always be at its correct position. So then E would stay as it is, A, B, C, D also would be stay as it is. So the array would remain same as it is. And every time you just reduce it by one position. So then the division would be like all the elements, like it here you can see it gets broken up into log n, but then in that case it would be order of n. Let's just see how it works. So if you remember, we saw that quick sort was the worst case was order of n square. Yeah, here. So for adaptability, we saw that quick sort average is order of n log n, but if it's already sorted, it becomes worst to order of n square. Let's see why. So you have this A, B, C, D, E. You select the last element as pivot and try to put all the elements before it towards the left of the array. So then your code will be A, B, C, D, and E would stay as it is. Then from the rest, you select the last element as pivot and put the rest as it is. So A, B, C, and then D stays as it is. Then say similarly for C, then similarly for B, and similarly like one more level down would be, can I go down? Okay, I don't know why, but yeah, one more level down would be A. So then it would be like, how many levels do you see over here? So from last to first, it will be E, C, D, B, A, one at each level. So your height of the tree then would be like one over here, just one node, and then all the whole nodes over here. The bigger chunk over here. Again, from the bigger chunk, one stays and the bigger chunk stays. So then it would be n times this happens. There is no optimization that would happen. Whereas in like average case, what happens is it's some random number, some random midpoint. When it gets, at least the height gets truncated a little bit, then one individually at each step. So then you can say that average case, it turns out to be order of n log n. Any questions on the time complexity? If not, then just let's see how the partition works. So yeah, from this step, we saw that D comes at its right position and then the lesser goes to the left and the more greater comes to the right. But how do we actually make from this step to this step? So that's what is depicted here. So you keep a pointer at its beginning of the step and compared the pivot element to all the elements from left to right. So you first compare, okay, let's do it on Sketchpad quickly. Okay, so you keep the first element, this is your pivot right now, which stays as the last element always, it stays the same. And you compare each and every element before it with the pivot. So, and maintain a pointer also, which is the current element. So E is less than B, which is true. So you don't do anything. You move to the next element and check C. So C is actually in fact lesser than D. So whenever it's a lesser element, you just swap it with the one which is on this point, the previous pointer that you maintain. So C and E get swapped. You get C, E, and the rest stays it is. Now if you compare the next element A with B, because your set was initially your set was this, then it became this. Now your set is this. So you compare A with B, and A is again smaller than B. So then swap will apply, where you swap E and A, and the pointer becomes at E. Now your code is only this much. Where you compare B and D, again B is smaller than E, so you swap E and B. So E comes here, B comes here, and the pointer also moves here. And that's when you realize you have exhausted your you are out of the loop, and it would ensure that the element which is here would be always higher than the one which is here. If it's not the last element, so then we just swap the last two elements. So that's how you get C, A, B, D, E from your original E, C, A, B, D. So you can see, like, you select D as the pivot, D comes to its correct position, which would be there. All the elements lesser than D are on the left, C, A, B, in the order as it appears in the input array, and all the elements which are greater, so E, which comes on the right. So this is one step which goes in between over here from like the first this to this. And then you apply it recursively on the left side and once on the right side. Any questions on this quick sort? Anyone? Okay, so going to the next, which is counting sort. I think this is one of the most interesting ones, where you have an additional memory where you index the positions from 0 to the maximum element you have in the input. So here you have 11. So you go from 0 to 11, which is n plus 1 element, that is 12 elements. And for each element, you just track how many numbers you have and put it in some sort of a bucket. So 2 is appearing one time, 1 happens to be 2 times. To maintain this list, and then again just iterate through the list to find out how many elements are there. Like 0 is happening 0 times, then 1 is happening 2 times. So you put 1, 1, then 2 is 1 time, then 3 is not 4. So you just create the array back again from your modified count sort. This is, I think, one of the most easiest and interesting ones. Any questions on counting sort? It's also called sometimes bucket sort.
Yeah, as I typed it in the chat, as long as you don't have like a huge range here, like from 0 to 100, or 0 to 1,000,000, actually, then this is a really great sort. So just be careful about that.
Yeah. And the next is Reddick sort, where you look at each number, like you first normalize all the numbers which is given in the way that it has the same number of the most significant bit. Like if there is just 8 number over here, then you make it 008, since the maximum number is 3. If there is 90 over here, then you make 090. And say if it is 1000 over here, then you make 1000 and all the elements over here is 0, like the most significant bit. So you first normalize it to make all the elements as the same length, and then start from comparing least significant bit and put it at its right position. So just considering the least significant bit as this, 720 is the minimum, so you put it as first, then 0, 5, 6. So you sort the numbers based on that. Then move to the second least significant bit and try to sort it according to the second bit, where it is 2 are smaller. And this is where stability comes into picture. Like you have 2 elements with 2. So what would you do? Would you just put 329 before 720 or 720 before 329? So whatever comes into the input first will stay in the output as first. So 720 comes before 329. This is where stability comes into picture. So 720 comes 329. So you get the second sorted as in like this, and then you move to the third significant bit. You try to sort it. 329 again comes before 355 since it's happening that way. And finally you get the sorted one. Any questions?
Sounds pretty straightforward.
Yeah. So now quick quiz time. So if you want to check whether the input is already sorted or not, which is the best algorithm that you can apply? Anyone in the comments?
And Kesha put together like a really great list of questions here. I'd expect that you would get asked questions like this in an interview or on your midterms. And I think a lot of times when we're studying algorithms, we're kind of like, what's the point? Why are we doing this? And it's really so that you can choose the most appropriate one for different situations. So if you're looking at this and you're focused too much on the implementation, you really want to step back and think like, when would be a good time to use each of these? So for the first one that she asked, if something's already sorted, which algorithm would you want to use, or what would you at least want to look for in terms of the time complexity?
Anyone? Just any guesses? You can unmute yourself or put in the chat. Yeah, counting for 5, 4, 3, 2. Okay, yeah, Grace. What's your logic for bubble or selection?
I guess because if you do like bubble sort, then you're moving everything, like you're gonna be like moving the maximum all the way to the end. And so if you get all the way, actually maybe not bubble sort, never mind, because that's like n squared. But I was thinking the selections, nope, both of them are n squared. But
You're going in the right direction.
I go like through the whole thing with like no swaps, but then it'll still go through it n times.
Yeah, no, I think you are going previously in the right direction. So for bubble, you can just ensure if it's in the right direction or not. But selection, you always find the minimum and swap it at the first position. So even if the first element is the minimum, you swap it with itself. So then you would do it for all the times and check for the minimum in the entire way. So selection is definitely out of the picture. Let's see how bubble works. So if you remember, we saw in the bubble implementation an extended code where we first initialized a variable sorted, making it false. And then in the first loop, say it becomes true. You only make it false when there is at least one swap. So if there is no swap, means it's in the sorted order. And so the sorted will remain true when there is no swap. And if it go inside this, any of this for like jth iteration, it comes here, sorted stays as true, and then not of true would be false. So then it will break out of this loop. So just once, if it encounters whether it's a sorted, then it will just break out of it. So you don't need to go and check for any other elements once it's known to be sorted. So then it just breaks and collapses to just one iteration. And whereas for selection, you said, yeah, we find the minimum and then we check through all the elements from I+1 to like n, see the minimum and replace, even if the j and minimum are, I and minimum are same, we swap it. So then it goes for order of n square for all. Yeah, good job. Yeah. Then suppose you have a stream of numbers incoming. So you have initially just say 5, then you have 5, 3, then say 5, 3, 4. So which algorithm would be the best. Okay, countdown again. 5, 4, 3, quick sort. Okay. Quick sort, what benefit do you see?
That's a good question. If you have 5, 4, 3, 2, like, because then your pivot would be 1, and so then you'd move all of them over. I don't know if that'd be the best one.
Yeah, that's definitely not a bad one. A good choice, because then the half of inputs are already sorted. But then if the later element is, say, initially you have 3, then comes 5, then comes 1. So then 1 would need to go at its correct position, and then it gets divided into 2 parts. Then say you have 2, then it gets split into 2 parts. So you have to again call it, even though you have found that it's lesser, but you have to call it recursively in 1, 2 as well. But you know that 1, 2 is already sorted, but quick sort will go and try to sort it again. So that is okay, not like the worst part, but there's also a better algorithm available where you have insertion sort, which looks at only the first element first. So E stays at is, then BE gets into consideration where it comes at the right position. Then CEB gets where C gets in the right position. So you imagine it as a stream of numbers, like 1 gets added at the right time, and then it goes in the right position. Make sense? So one number which is getting added every time. You have E only over here. Just forget the part over here. Just imagine there's just one E. Yeah. So imagine there's just one E over here first. So you have one element. Then you have E and B, 2 elements where it comes as a stream. So B comes after E. So you put B as at its correct position. So BE becomes the result. Then you have one more element C. You try to put C at its correct position, which would be between B and E. So you have this much. Then you have A incoming. So you put A at its correct position. The result becomes this. Then you have B, where you put B at its correct position. So it loops like that. Then the third question is, which algorithm will always ensure order of on n log n in best, first, average, everywhere? It would be like n log n. Merge sort, yeah, that's right. Merge sort is correct. Then what if you have input in fixed range, say 0 to 100, which algorithm would you use? Count, yeah, that's also right. So you have your count as 0 to 100, which is 101 elements, and put it in the buckets and then retrieve it in time. But what if like your range is having negative numbers, like coming from -100 to +100? You modify the count sort. Is it possible to have a -100 index for the array? So any other algorithm you would prefer, or you still go with the count sort? Five, 4, 3, 2, 1. Maybe we can just create a, I don't know how to create polls. Okay, any opinion about, like, you would continue with the same count sort or move to a different sort, different type of sort? You would try to modify it, or you would think?
Could you modify the count sort? You would just increase the values by like 100. Would like would you? I feel like you would change the values of the original array to make them a pot, like start at 0, and then, or at least you could calculate all of the counts and then convert it back at the end.
Yeah, that makes sense. So I'll just put a small example where you have minus, say 5, 0, 1, say minus 3 and 5. Then you will have your range is between minus 5 and plus 5, which is like 11 elements. So we'll create an array of 11 and put like minus 5 as a new index to 0. So you'll just add 5 to every element plus 5. So 5 would be 1. Like in the 5th index, you'll put 1, 10 plus 5. So 1, so 6 would be again a 1. Minus 3 plus 5 would be 2. So then while putting into the index, you just add the minimum element. And while retrieving, you will subtract the minimum element and put it back. Make sense? Yeah. Okay. And what, okay, so what if you don't want, what is an algorithm that you'd use if you don't want to directly compare the whole numbers by themselves, the input numbers by themselves? Any sort? Like if you don't want to compare the whole numbers as it is, like here you compare, say, the entire E, like here you compare the entire E element with C element and then D element with, say, E element. So the whole number should not be compared with each other, but like maybe a part of number should be compared. Any idea? You split the number in some way and then try to see. Oh, sorry, I missed the chat. Radix, yeah, correct. Radix sort. And any limitation of radix sort? Any limitations that you can think of radix sort? So it does not work well with negative numbers. Yeah, sorry.
I was gonna say too, like if you'd have to convert the length of the numbers so that they all match up.
Yeah,
like
so
if you had something that had like it was just tens and another that was hundreds, you'd want like there still to be a 0 in front of the tens.
Yeah, but you can always normalize it to make 10 as 0, 1, 0. But like if it is a negative number, then you cannot compare it and put it at the right position, because then the ordering would not stay the same. Say you had minus 436 over here, then there's no way to find out that minus will stay up, and then you have to again run radix sort onto 2 buckets to divide the total array into 2 buckets, negative and positive. Convert all negative numbers into positive numbers. Keep the positive numbers as it is. Run the radix sort on both of them individually, and then try to combine them in such a way that you again put a negative, convert the negative into again, like since the negative was already made a positive, you convert it back to negative, put them on top and put the positive on bottom. So that would be a little complicated for radix sort, but yeah, not a straightforward. So that's a limitation. And binary search is one of the use cases where you look up into the dictionary into half and then try to search into like left half and right half. So it only works when it's a sorted array. So whenever you want to search, if it's a normal array, unsorted one, then it becomes order of n, where you have to check through all the elements, whereas for binary search, it's order of n log n. You can see like it checks for whole, then it goes to the middle and discards one portion, then moves to again the middle of the second portion, discards one more portion, and then finds the portion where it is looking for. So in the interest of time, like if people have about 20-ish minutes more, 15-20 minutes more, then we can try to solve some lead code problems. Like not a mandatory thing, but people want to stick around, I'll continue solving some lead code problems if that works.
Yeah, and just I know I shared a survey, but it looks like it's not it doesn't have access for y'all. So I'm fixing that right now. I will also post it in the channel and I'll try to fix it and post it now. But essentially, we're trying to run these sessions for you all. So be kind, but also give us feedback on how we can best support you. So I'll update that and repost the link.
Yeah. And there's one problem on lead code where it's just sorting an array. You are given just an input numbers and you have to sort it. So as a homework takeaway, what you can do is apply all the different algorithms that you have learned and just try to get accepted on this problem, 912 problem. And it would be a really good challenge and would prep you up for the tomorrow's midterm exam. And then if you still have time, then try to do it in descending order, but that's an optional, but try to do at least all the algorithms on this particular 912 problem. And this is the cheat sheet that Sarah has pinged. So thanks, Sarah. I hope everybody fills in and has the ready reference for all algorithms. So yeah, I think not 3, but at least we can just do a couple of one problem at least, the merge sort, and then I can just discuss the approach for the next problems in next 10 to 15 minutes. So yeah, people who want to just drop off or have other commitments, all the best for your exams. I wish you very good luck. And for the rest of the people, let's continue and stick behind solving some problems. All the best. Okay, so the first problem is merge sort. So extending on the concept of merge, so you have it divided into 2 subarrays and you are trying to put them back together. And we saw that it's a separate temporary array that you make to put the elements together. But now this question given is saying that you have given 2 arrays which are already in sorted order, and the first has some space in the end, like it has zeros appended equal to the size of the second array. And now you have to merge them together and create a sorted array like this in the end in maximum order of n. This is like a twist of merge sort where you have partially sorted inputs and you make a completely sorted output out of it. So anybody who would like to just discuss the approach? What do you think? How should we go about it? Other input example is like if you have just 1 in the first array and empty in the second array, so there is no zeros appended since the second one is empty, and just you say that that's the result and you are done. The other case is when you have just 1 0, could be a 0 of itself or could be like a possibility to merge into 2, the second array. And since the second array has 1 element, you try to put it at the first place and just say I'm done. So how do you like merge 2 arrays where there are some zeros in the end and you try to put merge 2 arrays which are partially like individually sorted? Grace or Lydia? Sorry, if I don't pronounce your name correctly. Would you like to share your thinking process? So a hint could be like instead of viewing the arrays from left to right, try to see from right to left, and if you can fill up. So you know over here that n is of size 3. So you have this much, and n is of size 3. The minimum element could be anyone, and then if you try to fill it from the start, you could like bump into one another. But if you fill it from the end, you can just compare the last elements and see which one is maximum. So from this 2, 6 is maximum. So you put 6 as the last element, which is like fixated, and then your sub array gets shortened to 2, 5 for the second and 1, 2, 3 for the first. So maintain 2 pointers from the end and try to see which one is the maximum one, put it at its correct position, and then move forward till you reach the starting of the array. Make sense? Yeah, just let's try to code it. So you are given m and n. So your final length of the array would be m plus n. And final length would be m plus n. And since we are dealing with 0 indexes, it would be like 3 plus 3, 6. Okay, yeah, 6. And since it is like 0 to 5, so minus 1. M plus n minus 1. Make sense? And m is also like, even though it's 3, for us it is 0, 1, 2. N is also 0, 1, 2. So this m and n are given as one index, so we'll just convert it to 0 index by subtracting 1. We have 1 subtracted from each. And now we try to compare. M is right now, so taking the first case, m is right now 2, n is also 2, and then is 5. Now you want to do like for or while at least one of them is not exhausted. So while both are existing, where m is greater than or equal to 0 and n is greater than or equal to 0, like we saw in the merge, we have a condition where both of them are existing, then it would fall out when one of them becomes negative. So we'll handle for the case where both becomes, for any of the case where it's remaining, we'll put it. And here we'll just put the pointers nums1. The final length is this pointer, so we'll just set as this pointer is equal to whichever is the minimum. Yeah, so whichever is the minimum, nums1 of m is less than nums2 of n, if whichever is the maximum. And also subtract 1 index since we are considering it. And since we have fixed the final position, we'll also go to the next final position. We'll do this till either one of them falls under 0, and then for the remaining one, we can directly set to the one which is remaining. So if nums1 of n minus minus, and nums1 is nums2 of n minus 1. So yeah, this is the result, and we can just run it on the test cases we have. And we'll just submit. Yeah, so it's accepted. And yeah, again, this is like with 100% better than all the other solutions. It's the quickest form possible. Okay, yeah, I think we are done for the session then. Welcome.
Sounds good. Thank you so much, Kesha.
Yeah, I'll be sharing the slides on our Slack after this.
Okay,
Thanks,
I'm gonna
Sarah.
stop the recording.